Hello, everybody. So I had an adventure a few months ago. There I was editing a large piece of code, trying to refactor some old code and bring it up to date. We had updated a library and obviously nothing was working anymore. So I spent a lot of time digging through several thousand lines of code over, I believe it was 3 days. Near the end of the third day, I had a magic realization that, in fact, all of the code I was desperately trying to refactor was, in fact, dead. Nobody was using it. It was unreachable. It was useless. I could have spent 20 minutes at the start of the first day deleting the code and carried on with my life. Dead code is not just something that you should not care about, right? It's just something in the background. Nobody cares about the code. It's fine, right? It's not. It is debt. It's as simple as that. It's one of the forms of debt in modern code. And I'm going to take a little segue before I get into ScalaClean itself to think about this problem. The weakest link in the system when writing software is this puppy. Several pounds of greyish matter that hasn't changed much in the past 200, 300,000 years. We are always worried about what it can do and the limitations of what it can do. Fear isn't the mind killer, as you get from June. It's complexity. We have to keep track in our heads of what the code is doing and what it should be doing and why those two don't match up when we're debugging. So let me walk you through another recent example here. So here's it's a bit pseudocode-ish. This was actually some Java code I was dealing with. But it's simple, right? It gets some values, it adds them to a cache, and then it filters them and does some other stuff with it. Except that you and I, as Scala developers, look at this code and already it smells a little. There's clearly a mutable cache somewhere in the middle. But actually, it had multiple issues. Get values can, in this case, return null because that's the standard Java convention for this stuff. So, in fact, line 2 might null pointer, not just add it to a mutable collection. Is the collection thread safe? Is it safe to add it here? Do I need to put a guard around it? Don't know. And last but not least, is the collection mutable? So these three things together leave us in a situation where we don't actually know much about the code. Now, and it's all about the cognitive load, right? Less really is more. We get away with a lot of stuff because as developers, especially as Scala developers, we have a bunch of defaults in our head. Less really is more, right? What do I know when I look at this code as a Scala developer? I go, well, get values will not return null, right? It will return, if it's optional, it will return an option, right? We don't put null in our code base. A null pointer exception is an anathema. Right? Okay, the cache might be mutable, but let's not worry about that. But I also know that collection by default in my head is immutable. So the collection.filter or someone else pulling it from the collection and doing something to it, I don't need to make defensive copies. I don't need to defensively copy as I put it in. I don't need to put other protections around it. That stuff just works. And it works because we've defined a set of defaults in the way our language works, and those defaults reduce our mental load. So then, what's the real question? Given a code base of any size, can we programmatically improve it? Can I do pure transformations that take an existing code base and turn it into a new code base that is in some way better? Now, let me be clear. When I talk about pure refactorings, what I mean is it mustn't change the behavior. The code might compile, it might be valid, and at the end, but it might also be wrong. It might have bugs in it. But this process shouldn't introduce more bugs. But also, can we make the developer's life easier? As I said, this is a game about cognitive load. What can we do to take source code we have, millions of lines, in our repositories around the world to make them a little better? So let's suggest some things we can do to reduce the overhead of managing the code without changing the code at all. We could remove all the dead code. As I said, I had a fun experience, wasted many hours, and I've wasted many hours of my career trying to fix things that didn't need fixing, or trying to understand things that were never used. So in any normal program, classes, methods, variables, parameters that are unused can be killed, right? And in fact, this is recursive. If I find a method that's unused, it calls things. Anything it calls that are no longer referenced can also be removed. So it's entire subtrees. It's not just cognitive load. Removing code makes your compile faster. It reduces, what we do and how we do it. It makes life easier, both on the tooling and in our heads. We just refactor it away, right? This is something that a program can discover and remove. So another option, privatization. One of the amazing things about a modern IDE, I hit dot and it says, here's some things you might want to do. But if you've ever used some code, sometimes the list is bigger than the display, right? It's a huge list because the API has far too much stuff public. Right? You don't know which the real methods you should call are and which are just the internal machinations of the code. So as a quality developer, as I'm sure you all are, we start to make things private. We reduce the scope and the visibility to make our lives easier. So we do this automatically. And in fact, if you look in Intellij, and I'll come back to this in a minute, it will suggest things you can do. It will suggest that this method is uncalled and maybe it can be removed. Great. It will suggest reducing the scope of some things. So, as I said, why we're doing this is this doesn't change the meaning of the code. It doesn't affect how the code runs. If it did, you've just broken the code. If I make something private that needs to be public, then the compiler is going to complain, right? That's it, job done. But it gives us better completions and better ideas. So this was the start of the idea about ScalaClean. Given knowledge about the code, not changing the meaning, the behavior of the code, and we'll come back to static analyzers that do that. What can we do to make the code easier and better to maintain? Once we have information about the code at a meta level, what can we do with this? So before we dig into that further, I'm going to introduce myself briefly. So I'm Rory. I've been writing software for over 30 years. As the introduction said, I've been at Morgan Stanley for the past 5 years, working on the Optimus platform in Scala, doing a lot of systematic optimization. Things I really care about are, from a technical perspective, performance and scalability. How do we make code run well? But also, I'm really interested in the human aspects of that. How do we make code that's maintainable over the long term? And each language choice we make, we pick a statically typed language because the compiler helps me more. We pick Scala over Java because the type system and the defaults within it make our lives better. Those choices and those trade-offs really interest me. What can we do as software developers to make our lives easier, to allow us to be more productive and focus on the fun stuff? I'm an open source contributor. I've done a lot of drive-by optimizations. Some people will tell you on random projects that I've touched. I like making things fast. I've done a bunch of work within the Scala compiler and within the Scala collections, which is all fed into 2.12 and 2.13 and into Dotty, which is awesome. And I love the fact that as a Joe Blogs on the street, we can all contribute to this stuff. Right? Go and get involved, ask the questions. People love having help. And as a random aside, I also give tours of a local windmill in Sussex. So if you're ever down in the Sussex Downs, come and find Jill Mill. So now what I need to do is define what I mean by static code analysis. Now, we already know the compiler does some of this, right? The compiler's job, the Scala compiler's job, is to validate the code and turn it into executable code, bytecode. So it does some static analysis. It looks at the program as defined and then transforms it from Scala code through the AST into bytecode to be run on the JVM. But static analysis says, well, that's true, but let's take a step back from, a compiler's worried about turning, making sure the code is valid and turning into executable code. But we can take a step back from this. We can view code as a data structure, right? A method calling another method is an edge on a directed graph. Based on that, if you think about your program, your entire program and its dependencies as a graph, then we can apply graph analytics to it. We can explore the graph for problems and opportunities. Right? It's not just making the code compile, we can infer things. In fact, the Scala compiler already does this. One of the talks earlier was talking about metals and talking about Scala 3 and saying unused imports are coming in metals for Scala 3, but they're not there yet because the compiler is the one that reports those things. In Scala 2, it's a compiler warning that an import is unused. The reason for that is it's really easy to detect that at the point of compilation. Right? I know all of the things that a given piece of code references, and I can see if the import is used. Great. So, as I say, the compiler, in a typed language, a compiler is already doing some static analysis. You've called foo. Does foo exist, and is foo valid to be called at this point in time? But that's not the only analysis we can do. In fact, there are already loads of static code analyzers that do different things. Let's walk through some. So an oldie but a goodie, find bugs, or I think it's called spot bugs now, is something that will look at your code. In fact, it looks at it at the bytecode level and notices things about your code that are probably bugs. If you can prove that this is going to throw a null pointer exception, I set A to null on line 1 and then I try and do a.foo on line 2, you can detect that and you can flag it as a probable bug. Maybe that's what the developer wanted, but it's unlikely. Other ones, PMD and the related CPD, the copy-paste detector. Again, tools that look at your code and try and find useful things. So there are loads of these. SonarQube, but you've also got things like Scala format and ScalaStyle, which look at the structure of the code and convert it or complain about it depending on how it's set up. For Scala, you've also got WartRemover, which is a fun one. So, and your IDE. So in your IDE, I'm sure you're all very familiar. If you're using Intellij especially, you get the little yellow icon in the top right and flags down the side of your code that say, are you sure this is what you actually meant? Inspections are great. I love them. I generally aim for 0 warnings down the side of my Intellij because that's what I want. The problem is these inspections tend to be shallow. What I mean by that is Intellij will correctly flag that a private unused method is unused. But if it's public, it won't flag it. Right? It may, I'm not sure that's entirely true, but it's true in many cases. Right? So it does some things. It spots obvious things. It spots some actually fairly subtle and non-obvious things. But the detections that it's doing are relatively shallow. They're localized. Where, for me, we want to do something more interesting is at the whole program scope. So rather than spotting useful things locally, null dereferences, simple unused methods, unreachable code, great. But can we do this bigger? And the answer is yes, you can, but it's going to require some more heavy computation that you probably don't want to do in a presentation compiler. So then what is ScalaClean? ScalaClean is simply an exploration of static analysis. It started with me and a guy called Mike Skells, who were like, can we do this? Can we detect this stuff? This irritates me. This kind of stuff niggles at me. So what can we do? And actually, you can do some interesting stuff. And I'm sure there are use cases and opportunities that we haven't thought of yet. It is absolutely a work in progress. It runs, it deletes code. I'll come back to what it does and how it does it in a second. But it also has some issues. It's a little too aggressive, let's say. It will, if it determines something is dead, it will delete it. But really, the last point is, what can we discover about our code that we can't just get by inspection? What I find is when you're inspecting code, you look at a given class and you're trying to get an idea in your head of the interactions. And at a point in time in my IDE, I can say, who calls this or who does this call? But I can't see the big picture. I'll give you an example. Code that's only called by test code. That might be valid, right? It might be a test entry point into the code that you might need, but it might also just imply that code that's evolved over time. And yes, that code's tested, great, but it has no use. It has no value, right? I've got a test that takes time and effort, and I look at results and I look at my coverage. I go, my coverage is awesome, except that it's covering stuff that doesn't matter, and the key things that I do care about aren't covered. So really, what can we discover about our code? So, ScalaClean is actually fundamentally really simple. All it's doing is capturing relationship information. So how does it do this? Well, it's a compiler plugin. So we have a plugin in the compiler that runs at a later phase, and all it's trying to do is capture information that in fact the Scala compiler is throwing away. The Scala compiler has it at some point, but it's not relevant for outputting bytecode. Right? Once you've determined that A equals B, you write into bytecode, A equals B, but you don't need to worry about it anymore. As long as it's type checked, you've done all the stuff in advance, what the compiler cares about is outputting what goes into that file. So we capture, when you run a compilation with the compiler plugin attached, we capture 3 different pieces of information. First off, we capture the elements. Now these are like the method definitions, the val and var definitions, the interface definitions. One of the key things that we do is we capture the positions of these things. One of the pieces of information that the Scala compiler throws away is exactly where your method is defined. It doesn't need it for bytecode. Bytecode, in fact, if you look at stack traces, when you have a stack trace for complex mapping operation where it's got multiple things chained together, it will say, I had an error on line 54. And sometimes that's really hard to debug because line 54 can have 15 statements on it, because we're really terse and can do really clever things. So we need to effectively capture information that existed in the compiler in the earlier phases, but is lost by the time it gets to bytecode. So this kind of work, some of it can be done at the bytecode level, but a lot of it can't, especially if you want to then go and edit the code afterwards. Saying there's a bug on line 54 is great, but actually then rewriting line 54 later, you need to know a lot more information. So we capture the elements, we capture what they are, their fully qualified names, and where they are. We also capture relationships. This method calls this method. And I think that's fairly self-explanatory. And last but not least, we capture extensions. So this is metadata. This can be annotations. So for example, if you're using dependency injection, you often use annotations to define where your entry points are. So that's all we capture. Right? What we're trying to do is two things. One is reconstruct the call graph, the graph of the system. And the second we're trying to capture is where the relationships between those are. Once we've done that, we can actually generate a relationship graph. We can generate a bidirectional graph, callies, callers, and all those parts. So that part's fiddly but mechanical. What's interesting is the next part is actually quite easy as well. We traverse that graph. If you think about how garbage collection works, it says, given all the entry points, given all the stack and the static variables, mark all those as valid, mark all those as live, and then mark and sweep, traverse through the graph, marking each thing in turn, recursively. When you get to the end, everything that's not marked is dead and can be garbage collected. So it's a graph coloring. Now, the interesting thing for us is, depending on what you're doing, the coloring is different. If we're doing dead code analysis versus privatization versus other things, the colors you have and the colors you use, the colors that you apply are different. But fundamentally, it is just graph coloring. And we'll come to a couple of the bits of complexity in a moment. And once you've got that analysis, once you've visited the entire graph, if from an entry point I can't get to a method, that method is dead. So I can then edit the code and remove it. So one of the challenges, as I said at the start, is we need to capture enough information. The class files at the end don't contain all the information from the original code. In fact, the Scala compiler by the end has thrown away most of the information because it doesn't need it. Right? It needs to generate enough information to generate good error messages, but it doesn't really care where the keywords are. It doesn't really care whether there's a new line before or after the word private. If you want to remove a method, though, you need to know exactly where that method definition and all its metadata, that's the comment, that's the annotations, all that stuff, you need to know exactly where the bounds for that stuff are. And that was one of the fun parts of the original implementation. Syntactic sugar's a pain. The compiler's job, as I've said before, is to compile, which is great. It does a really nice job. It does it really fast. We love it. Keep it up. But it has some hacks in it. So one of mine, for example, is for comprehensions are syntactic sugar over map and flat map. What this means is that earlier right in an early phase, it gets rewritten internally. And you have to go and look not at what the code says now, but what the attachment said that the code looked like before. So there's a lot of fiddly edge cases because the AST cares about the structure, not about the original code. It's a semantic value, not a syntactic value. Macros are also a pain. Macros are a pain specifically because there's effectively two versions of the code. Right? There's the thing before macro, the macro rewrite, and the code after the macro has been rewritten. So when I'm dealing with graph coloring, the macro says .foo, and I rewrite that to a bunch of code that calls bar and baz. Well, do I now need to color bar and baz, or do I color foo? And there's some trickiness in there. So we've gone through, we've marked the code, and now liveness, as I said, is actually sort of easy. So where do we start? Well, a main method is implicitly alive, right? This is like a root in your garbage collection tree. Right? Any method it calls is alive, right? And so on recursively, right? We can just follow the links and mark things as alive. They are directly reachable. Now, let's be honest here. That may not be. There may be dead code even in code that is reachable. There may be branches. A classic example is flags that your application takes. Right? If the flag is on, do code X. If the flag's off, do code Y. Those tend to rot over time. People flip a flag, they put in a development flag, but they forget to remove the flag afterwards. Right? It's always on or it's always off in production, which means some piece of that code is dead. It might be tested. It might have a unit test to test both branches, but in production, it never runs branch 2. So static analysis can't tell everything. As I said, it's similar to mark and sweep. You're simply following through the graph and marking them. But it does get more complex, and this is where the fun begins. This is where actually working out what the right answer is becomes a challenge. Let's start with an interface, right? So the interface is live. The method we care about is called, but it had to be live. The method both needs to be called from somewhere, and the containing class needs to instantiate it. If I have a method on a class which is never constructed, it's dead, even if it's so I've got two classes both implement an interface. One of them it might be dead on. So actually working out the exact rules is a bit of a fiddle. Then you get to other places. I've mentioned this earlier. What about test code? What about code that's only called from the test, from tests? And this is a very common case that I've found, which is code evolves, but you don't go and delete the tests because you're not sure whether this is used or not. So the test is still there, the code is still there, nobody flags it because the code's got a test, right? It's called from somewhere, but it's never called from live code, which means it's really dead. It's just a tax, right? It's a tax on running the tests. It's a tax on executing, on compiling. You've also got reflection. So, I can't detect something I can't see. If a piece of code is called via reflection, then you need to handle it in a slightly different way. Dependency injection entry points are the same thing, right? They're effectively reflection. So there's a whole bunch of cases here which you need to handle, and we need to handle as developers rather than as software, right? I can't tell that the DI framework is going to call this code. What I can do is I can annotate it. I can also teach, for certain cases, you can teach ScalaClean what to do with these things, right? If it recognizes you're using Spring, it can look for the Spring annotations and go, this is Spring, this is live, I can do this. So as I said, fundamentally, what we're doing is relatively simple. Find the call graph, color the call graph in various ways for various purposes, and then do something with the data that's left over, things that are either colored or uncolored that you want to do something about. We've actually done this at scale. Right? What we've seen is that when we've run it on code bases, that we often see a 20 to 30% reduction in the code size, which is really quite fun. If I said to you, well, you've got 100,000 lines of code, which is quite hard to maintain. If I said, well, it's now 70,000 lines of code, right? It's much less for you to deal with. It makes your compile. We talk about, if you get a 2% compilation speed up in the Scala C, people are ringing the bells and shouting from the rooftops. But if I can delete 30% of your code, then your compiler is going to be significantly more than 2% faster. So let's go bigger. One of the fun parts, as I say, of working at Morgan Stanley is I get to play with the Optimus code base. The Optimus code base is a large code base. Last time I checked, there are about 16 million lines of code in the monorepo. About just over 8 million lines of them, I believe, are Scala at the last count. So how do we run this on Optimus? Well, it's actually really simple. We integrate the compiler plugin, even with OBT, which is the Optimus build tool, which was talked about in a talk earlier on in the year. We run the build, right? This is a static analysis thing, so we don't actually care about running the code, we only care about running the build. And then we analyze the results. So that's actually running the tool, and we'll come back to that in a second. So I say, ScalaClean is two parts, the plugin and an application. So we integrate with the Scala compiler, right? We need to turn on two sets of flags. The first one is -y range pos. That means the compiler contains information about extra positions. You'll find you need that for metals and various other tools as well. And secondly, we need to tell ScalaClean where the source directories are. That's one of these. It's actually slightly hard to determine from the point of compilation where your sources are. So we actually tweak that in the compiler. I've got to give Dale from Lightbend a big shout out at this point, because he helped me a lot with his SBT foo to get it running in the project with lots of test projects and making all this integrate beautifully. So thanks for that, Dale. So in OBT, it's pretty similar. This will be the similar for mill or your build tool of choice. We can simply add the flags and run the build, because at the end of the day, everybody runs at some point the Scala compiler. So running it, as I said, is just trivial. We just compile, and it spits out a whole bunch of stuff into the target directory. So now we get to the analysis phase. Now, there are actually multiple main methods in ScalaClean, depending on which tool you want to run on the code, whether that's dead code analysis, privatization, or what we call simple dead code, which I'll come back to. So you run the app. Now, for 8 million lines of code, I'll be honest, it took a while to run. In fact, the first time I ran it, it crashed. I'll be honest, the second time I ran it, it crashed as well. But with a few iterations and a few tweaks to the flags, including quite a lot of memory, it's a really big, because it's effectively a mono app and a mono code base, it took a lot of memory and a load of time to run. But do we care? That's fine. We're not necessarily needing to build this into every build cycle. And it could be made faster. But at the end of the day, it's now containing a bidirectional graph of every call within the application, a whole bunch of metadata around it. So it made a lot of changes. So the default dead code analysis actually goes and changes the code where it sits on the disk. So if you are going to try it, caveat emptor, beware. commit your code first and then run the tool over it. Don't, because it broke it. I'm not going to lie. The first time we ran it, the code no longer compiled. This is, it deleted some live code. As I was saying before, actually working out what is live sometimes can be quite hard. Right? You know, when we think about apps, we think, oh yes, you've got a main method and some things you call. Great, that's easy. But in fact, there is code that's called from Java, code that's just a library, right? It generates a jar. There's no main method. There's no entry point unless you annotate that class as an interface that says this is a public interface. ScalaClean was a little too aggressive and just deleted it for you, which compiled really fast, by the way, when you delete all the code. And there's a whole bunch of magic entry points. But interestingly, it did work. And it found when we, what we did is we sat there with git diff and we looked through the code and we, unpicked some bits, ran it again, fiddled with it, but it found quite a lot of dead code. In fact, it was about 15%, I think. So that's 15% of a 8 million plus line code base. It was great. It made things better. We actually committed a load of code to cleanups to the main line that made the code better. And that's the goal of this. It's not a turnkey solution at the moment, and it's going to take a while to get to that point. But even doing it manually, so we ran the code and then effectively we reverted changes that didn't work. And then we will add annotations and so on to make it, to stop ScalaClean doing it again. But it was an interesting investigation. It actually worked. It actually found a bunch of code that you're never going to find as a developer. It found entire subtrees of things that were simply removable. Where we struggled, down in the heart of Optimus, there's a bunch of high-performance Java code. Of course, relationships in there aren't correctly tracked. So it tried to do, it didn't see those and it promptly deleted stuff. As I say, it wasn't perfect, but it sort of works. And this is one of the ones I know I've mentioned it already. Those tests, test liveness is one of those interesting discussions. How do we deal with code that's only called from tests? Is that dead or is that useful? And actually, you would need to integrate your coverage data. Is the code that's being called from that, if what we're seeing as dead code that's only called from tests, actually then testing live code? Is it an entry? Is it a test entry point that's doing some useful work? So in ScalaClean, in the first iteration, we basically created an overrides file that said, here is a bunch of entry points. Given a fully qualified name, this is live, don't delete it, treat it as a source root. And it's not enough. What we actually need, that is really hard to maintain, which actually is never going to win, right? We need to make it so it's easy to do. So we need to add annotation support, so we can say, at live, comment, so we can add that to code base and make it more intuitive. So I want to talk a little bit about the development process and thinkings about that, because I think it's quite interesting. It's surprisingly hard to debug. One of the problems is that you are dealing with effectively the compiler's internal view of the code. You're generating metadata from that, and then you're applying the rule, and at some point it deletes some code and you go, oh, it shouldn't have deleted that, or it's got the position information wrong, or some other subtlety. And those subtleties are really hard to debug through that chain. Each of those chain steps effectively loses information and makes it hard to do. One of the nicest tricks we did is we have a mode that allows us to pump out metadata into files next to the original source file. So, for example, this piece here says this definition is overridden by these points. So you can actually just look at a diff. So when it changes, when the behavior changes, and in fact, for example, which I'll come back to in a second, when I upgraded from Scala 2.12, I think it's 5 to 6, it broke. The test started to fail. It's great having lots of tests, and we have lots of tests now, but they failed. And there'd been a subtle change in how one thing was handled inside the compiler, and it changed its behavior from a getter to a method. So this is fiddly, and it's fiddly to reason about. One of the things on my to-do list is to actually build an HTML report. So instead of trying to delete all the code, what I want is a nice HTML view of the code that I can navigate around, because I've got all the navigation information, and I can context highlight it and do all the rest of that stuff. But I can then add metadata, I can add hovers to show me the whys and the wheres and what's going on. And by adding that to a side-by-side view, I think this will make it easier. But in fact, I think the biggest challenge for ScalaClean as a whole, the fundamentals are relatively easy. As I say, it's a collect metadata, do graph walking, do some coloring, and then apply the results based on that coloring. But from a reality point of view, there are many relationships in a large code base. Debugging why this one is wrong is really fiddly. And what ScalaClean and the compiler both thought about this piece of code. So one of the next steps for me is to really build a viewer, and this will actually make editing the code, building ScalaClean easier as well, because it'll make it easier to debug. So there's a few things that we want to do next. Annotate liveness. As I said, I want to put annotations on to deal with things like reflective access rather than just a liveness file, which is what's there at the moment, to handle library entry points or reflection. HTML report. I think this is actually one of the biggest things I want to do next, because I think it'll show the most value. And there's a bunch of metadata I want to add to this stuff. So code that's only covered by tests, dead code that's, you've effectively got 3 levels of dead code, right? Dead code that's not reachable at all, dead code that's reachable by tests, and so on. So by actually being able to see that stuff, rather than it just being, I've deleted it for you, which is what ScalaClean does by default, or the dead code analysis does by default. I actually want to see it and be able to reason about it. And maybe I want to do it in an interactive view. Maybe this should be integrated with the IDE, so I can go through and go, actually, no, this is live. Now rerun the analysis. Right? So you can do this. It should be an iterative thing rather than it being a one-stop shop, bang, deleted half your code. Interestingly, there's no reason this can't be multi-language. What I've found when I've tried to find test projects for this is a lot of code is actually in different languages. It's not just Scala, it's Scala and Java. Or, there's Java calling Scala, Scala calling Java. It's not as pure as you would hope. What's interesting is it is easy to integrate other languages. Right? You build a compiler plugin for that language, it outputs a graph with the appropriate positional information. There's very little difference between what we're doing in Scala versus what we'd be doing in Java versus what you'd do in C#. They're all basically doing the same thing when it comes down to it. As I was saying before, I want to explore liveness. So liveness, for example, liveness based on tests. But also, what I might want to say is, well, I don't want to delete code that's been added in the last 3 months, because it might be code in preparation for something. it might not be finished yet, right? It might be merged or being a feature, but let's keep the code. So we can start to build in stuff from the outside to make this actually a human usable tool. I love the idea of this being gating. This becomes like a coverage gating level. Not only do you need 80% coverage, but you need 80% coverage on the live code, or you should have no more than 5% dead code. As I said, Git integration would be fun. And one of the things I mentioned previously is it's an interactive exploration of your code. It's not just a tool that you run and it deletes some code and says, I'm done. This really is a discussion between the developer and the tool to say, no, this really is valid. This is good, this is bad. Oh yes, we can kill off that. Oh no, we need that for later. Right? Those kind of discussions. But it's not just about what the edge place, and the place that's really fascinating is the joint between tests, coverage, liveness analysis, usage analysis, right? So take a JFR, find out what code's actually being called, right? And flag code that's never called. How can we highlight that data to make our job as developers better? So in conclusion, static analysis has not reached its potential. We have a lot of fun and interesting tools we can add onto our code, but I think we could do better. I think we can go deeper. I think full graph static analysis is a really interesting area. It's a human problem, not just a computer problem, right? It's about reasoning about code. There are lots of opportunities to make our lives better. Less is more. Less code is better than more code. And of course, come and play. All contributions welcome. It is, as I said at the start, a work in progress and a thought experiment, but I think it's an interesting one. And with that, I'm done. Thank you all for listening. Any questions?
Rory, thank you so much for that talk and for that wonderful overview of ScalaClean. And it seems like a lot of people are excited about this. We have several questions. We'll see how many we can squeeze in here. So the first one is, how is ScalaClean compared to ScalaFix? Can they be complementary of each other, or would it fight against each other?
They are completely complementary. ScalaFix is doing localized. This is what I say. ScalaFix is static analysis, but it's static analysis that tends to be localized. So by ScalaClean's view is to take the entire thing, the program as a whole, rather than individual components. And ScalaFix is a bit like the fixes in Intellij as well. It's those kind of like, this can be better, or this is clearly wrong. Where ScalaClean is trying to look at the big stuff. So they're absolutely complementary.
Brilliant. All right, next question. Can the bidirectional graph be visualized?
Good question. I would love to say yes, but yes, it could. And I'm open to suggestions on the best way to look at it. One of the ways I was talking is an HTML view of the code. But if there's these graphs are big, right? On a non-trivial program, these graphs are huge. So if you have suggestions on how to visualize those, I would love, please reach out to me and let's have a chat.
Awesome. All right, our next question. How is ScalaClean compared to Scapegoat?
I haven't used Scapegoat in a while. It's probably, honestly, a lot less mature. But again, I think Scapegoat is a much more point in time, these are code errors kind of detection rather than graph analysis. I think it does work at the AST level, but it's very localized.
Got it. All right, our next question. Could you run ScalaClean on an actual library repository, for example, by telling it which methods are the public interface?
You can. It's a little painful at the moment to do, and this is something we should explore more. Basically, that's what you need to. This is when I was saying that it often deletes code that it shouldn't. This is exactly it. We need to say that this class or this interface is, a public API. Don't delete it. And we need to improve the rules that allow us to say anything in this package is live, or anything in this class is live. Treat this as top level, and then it should be able to run on a library, not just an application.
Excellent. All right. Next question: is ScalaClean working, or will it be working for Scala 3 code?
It is not working at the moment. It does work for the latest versions of 2.12 and 2.13. For Scala 3, it will be working, but we've got to rewrite the compiler plugin.
Got it. All right. Can ScalaClean detect dead loops as well? That is, two methods only calling each other and not called by anything else. Scala compiler seems to be fine with that.
Yes, this is the key of graph analysis. Because it's graph coloring, you can effectively that cycle is unreachable. So therefore it never gets colored, so therefore we know it's dead. And this is one of the things that I was sort of alluding to before, which is simple analysis saying nobody calls this, it's easy to detect. But as you say, when there's a loop, when A equals B and B equals A, you can't necessarily detect, especially when the loop is complex. You might be able to spot it, but the compiler, or for a complex loop, you can't see it. So yes, it will, because it's think about it like GC. It's a dead loop in garbage collection.
Excellent. All right, I think we have time for one more question here, and this will be our last one. Do you have examples of what the HTML report would look like and how it would help you?
Off the cuff, do I have an example? No, but I've looked at stuff like SonarQube and other sort of HTML displays of code. I suspect it would look something like that. And how it would help me is think about when you're doing a pull request review and it highlights bits of code that are interesting, right? Or bits of code that have, in Optimus, we have, when you get a pull request review, it also highlights things that the internal tooling has detected as possibly problematic. So it's like the extra code warnings are at that level as well. So having those in the report, I think, would help you visualize what the tool thinks is going on.
Yeah, that makes sense. All right, Rory. Well, thank you so much. That's all the questions we have time for. Thank you again for your talk, and thank you for joining us at ScalaCon.
Thank you very much for having me. It's been a pleasure.
Absolutely.